In the surge zone of southern Australia, where the kelp forests lean and recover in rhythm with the tide, a shape drifts that defies simple classification. It is not quite fish, not quite plant, an apparition of green and ochre lace that moves not by will, but by waveform. The Leafy Sea Dragon exists in the shallow marine corridors where motion itself becomes camouflage. Each sway, each tiny oscillation of its frilled appendages is tuned to the pulse of the ocean's own breathing. To watch one for the first time is to question the stability of perception. Your eyes cannot quite decide whether it is alive or whether the kelp itself has chosen to move. The Leafy Sea Dragon's survival is built upon the physics of illusion. Its long, slender body mimics the blades and stipes of the kelp species it inhabits, complete with branching filigree that quivers in the faintest current. Unlike the seahorse, its close relative, it does not clutch to anything. It drifts freely, riding micro-currents between rock shelves and eelgrass patches, a suspended sculpture of vegetal mimicry. Each decorative filament is an antenna for deception, scattering outlines and refracting the logic of a predator's pattern recognition system. When a swell passes overhead, the dragon doesn't resist. It yields. Its movements are not independent, but harmonic, timed perfectly to the frequency of the water's push and pull. In doing so, it vanishes into the wave's own grammar, its wave-sync mask, a form of camouflage not rooted in color or shape, but in motion itself. To understand how this illusion works, one must consider the visual system of its potential predators. Reef fish and cephalopods, from wrasser to cuttlefish, are wired to detect contrast and acceleration more than stillness. Movement is information. A break in rhythm means potential prey. But the Leafy Sea Dragon offers no such break. By matching its motion to the ocean's surface dynamics, it turns visibility into noise. A predator scanning the kelp bed is confronted with a field of synchronized motion, all moving as one organism. Any single object that moves differently stands out. The Leafy Sea Dragon ensures it never does. Its mimicry is so complete that even advanced image recognition systems in modern marine research labs struggle to isolate it from footage of kelp filmed in natural surge conditions. From a physiological standpoint, this synchronization requires extraordinary control. The sea dragon's swim bladder allows it to maintain neutral buoyancy with surgical precision, adjusting gas volume in minuscule increments to hover without rise or sink. Tiny dorsal and pectoral fins flutter in near-invisible vibrations, about 30 beats per second, producing just enough thrust to counter drift while avoiding turbulent wakes that might betray its outline. Each movement is low energy and laminar, merging seamlessly with the surrounding fluid motion. It is not just hiding in the kelp. It is the kelp participating in the same dance of inertia and rebound dictated by the wave period above. This system operates most effectively in what marine physicists call the surge window, a zone where the energy of breaking waves is transmitted horizontally through the water column. Here, motion is neither calm nor chaotic but rhythmic, predictable enough for the dragon to sink, yet dynamic enough to create confusion in visual tracking. The animal's camouflage thus depends not only on its form, but on the hydrodynamic properties of its habitat. In tanks where water flow is static, the illusion fails. Predators can distinguish it immediately. But when the swell amplitude matches natural sea conditions, detection error spikes dramatically. In essence, the background, the oscillating kelp, becomes an active component of the animal's defense, a moving curtain that rewrites the very concept of concealment. Reproductive life adds another layer to this delicate existence. The male who carries the eggs must navigate this same surge without breaking disguise. The pearly orange eggs adhere beneath his tail, glowing faintly through the thin skin as they develop. During this time, his motion becomes even more precise, slower, subtler, a ghost within the kelp canopy. He will not feed heavily during this period, conserving energy to maintain buoyancy and station. The wave rhythm that hides him also threatens him, too strong, and he could be cast against the rocks, too weak, and the mimicry collapses. His success, and that of his unborn young, depends on staying within this narrow dynamic corridor, the perfect synchrony between biology and physics. The Leafy Sea Dragon's sensory world reinforces this dependence. Unlike the seahorse, which uses its prehensile tail to anchor and orient visually, the sea dragon relies almost entirely on flow cues. Its lateral line, a series of pressure-sensitive canals running along its body, acts like a mechanical sonar, detecting the minute accelerations of surrounding water. By reading the interference patterns between its own movement and that of the swell, it continuously corrects its position and phase relative to the kelp's motion. The result is an embodied algorithm, a living gyroscope that self-tunes to its environment in real time. If the wave period shifts by even half a second, its body sway compensates automatically. This feedback loop, honed by millions of years of evolution, allows it to remain nearly invisible in one of the most visually complex habitats on Earth. Yet for all its elegance, this strategy also reveals a paradox. The Leafy Sea Dragon's camouflage depends entirely on environmental motion. Stillness, its ancient ally in other species, becomes its greatest danger. On a day when the sea lies flat and the surge falls silent, the dragon becomes exposed, its motion now the only one in view. Some have been observed retreating to deeper ledges during these periods, hiding within shadow and reduced visibility. Others simply freeze, relying on color and texture alone. This vulnerability illustrates a truth about specialized adaptation. Mastery of one condition often means dependency on it. There's a deeper ecological resonance to this camouflage as well. The Leafy Sea Dragon's mimicry is not just survival, it's participation. By moving in synchrony with the kelp, it becomes part of a living wave circuit. Algae, water, fish, light, all oscillating in a shared rhythm. This harmony may seem poetic, but it has measurable consequences. The species distribution correlates closely with the healthiest kelp beds, making it a subtle indicator of coastal ecosystem integrity. Where wave energy and water clarity shift due to climate change, the balance falters. Reduced swell periods from altered wind patterns can disrupt the dragon's timing, increasing predation rates. Habitat degradation, too, robs it of the complex visual textures it depends on. In a research tank, scientists have tried to quantify the illusion, placing digital predators before footage of sea dragons moving in both calm and surge conditions. The results are striking. Detection accuracy drops by over 70% when the dragon's motion is synchronized to swell amplitude. This wave sync mask is not merely mimicry, it is a form of perceptual hacking. The dragon doesn't just blend into the background, it uses the background to distort how vision itself works. To the human eye, this mastery is mesmerizing, a slow, surreal ballet of fluid motion where biology becomes indistinguishable from the seascape it inhabits. Yet the question it raises cuts deeper than camouflage. Can the background itself become a weapon? In the case of the Leafy Sea Dragon, it already has. The ocean doesn't just protect it, it performs it. Each sway of kelp and flicker of light conspires in its defense, transforming mere survival into an art form shaped by physics, rhythm, and evolution's quiet precision. In the arid savannas and open woodlands of northern Australia, the line between motion and stillness defines the odds of survival. Heat shimmers off the red earth, and the dry leaves of eucalyptus trees rattle with the faintest breeze. Here, evolution favors not only the swift, but also the deceptive, those who understand how to manipulate the split second between perception and reaction. Among the dry creek beds and termite mounds, one reptile has turned this sliver of time into a weapon: the frilled lizard, Chlamydosaurus kingi, master of the startle economy. It begins with calm, an unassuming lizard, motionless against the trunk of a gum tree. The body is mottled in earth tones, almost identical to the bark's peeling layers. Its long limbs cling vertically, head pointed downward, tail tapering into shadow. It appears harmless, perhaps even timid, until the balance shifts. The sound of a goanna moving through the leaf litter or the sudden wing beat of a predatory bird. Then, in less than a tenth of a second, stillness erupts into spectacle. The lizard pivots, mouth agape, and a halo of skin unfolds around its head, a bright orange-yellow frill veined like autumn leaves and vibrating with motion. The transformation is instantaneous and shocking. A small creature inflated into a mythic figure, its silhouette doubled in size. The effect is primal, reaching directly into the visual cortex of any nearby threat. The frill is a cartilaginous structure supported by elongated spines connected to the hyoid bone, the same skeletal element that moves the tongue and aids in breathing. When muscles contract, the frill springs open like a living umbrella, exposing blood-rich membranes that amplify both color and heat. The mouth gapes wide, exposing the dark throat interior, a contrast that exaggerates the display's depth. To an approaching predator, this sudden bloom of color and size defies expectation. For the few moments it takes to process what has occurred, the predator hesitates, and in that hesitation lies the lizard's escape window. High-speed footage reveals that the frilled lizard often doesn't sprint immediately upon opening its display. Instead, it holds the posture for a heartbeat, watching for the predator's recoil or stutter step. This pause is tactical. In that frozen instant, neural confusion disrupts pursuit algorithms. The predator's brain must reclassify what it's seeing. Was that prey or something larger? Did it expand, or was it always that big? This phenomenon, known in behavioral ecology as startle display, is common in insects, amphibians, and cephalopods, but few vertebrates execute it with such mechanical precision. The frilled lizard weaponizes not aggression, but perception, forcing attackers to waste milliseconds recalibrating their strike. Once the delay is bought, speed becomes secondary. The lizard drops its frill, pivots and sprints bipedally across the red dirt, tail balancing its posture as hind limbs drive forward. It can cover 10 meters in just a few seconds, impressive but not exceptional compared to the reflexes of many Australian predators. Yet most never close the gap. The key lies in the startle economy, a measured investment of energy at the start of an encounter that multiplies the value of every subsequent movement. By spending a small burst of effort to trigger confusion, the lizard gains disproportionate distance and survival probability. The system relies on psychology as much as biomechanics. To test this effect, researchers have staged controlled chases between frilled lizards and simulated predators, both mechanical and organic. When the lizard deployed its frill, pursuers exhibited increased path errors, overshooting turns, delaying acceleration, or halting mid-pursuit. When the frill was restricted, escape success rates dropped significantly. The pattern mirrors predator-prey interactions across taxa, the same principles that guide a moth's sudden eye spot display or a cuttlefish's flash of polarized light. The startle effect doesn't just scare, it disorganizes neural processing. The predator's sensory system must resolve a conflict between prior expectation and current stimulus, and in that confusion, the prey vanishes. But this adaptation comes with trade-offs. The frill itself is costly tissue, vascularized, exposed, and vulnerable to heat loss and tearing. Deploying it burns energy and interrupts respiration, since the same muscles that open the frill momentarily restrict airflow. This means the display cannot be sustained for long. The lizard must calculate its use precisely. Flash too early, and the predator adapts. Flash too late, and the escape route closes. Timing is everything. Field observations suggest that frilled lizards often wait until the predator is within 2 to 3 body lengths before deploying. It's a dangerous game of chicken, but one tuned by millennia of trial and error. Thermoregulation plays a subtle role in this drama as well. The frill's surface area can also serve as a heat exchanger. In cooler morning hours, slight extensions help absorb solar radiation, while in peak heat, partial deployment radiates excess warmth. Thus, an organ of fear becomes, in quieter moments, an organ of balance. This dual use exemplifies the efficiency of desert evolution. No adaptation serves only one purpose for long. Even the sprint that follows the frill's display reflects thermal calibration. Frilled lizards reach peak performance around 36 degrees core temperature. Too cold, and their reflexes lag. Too hot, and coordination falters. The act of basking, waiting, and shocking must all fit within a narrow physiological window. Ecologically, the frilled lizard sits at an interesting tier. It is both predator and prey, feeding on small insects, spiders, and occasionally other reptiles, yet hunted by raptors, snakes, and large monitors. Its defense strategy embodies an evolutionary middle path, neither armor nor venom, but theater. The frill is not just a bluff. It's a controlled psychological explosion that buys survival time in ecosystems where most encounters are decided in under 5 seconds. The Australian bush favors speed and surprise, and this lizard uses both, not to dominate, but to disappear. The display also plays a role in social and reproductive behavior. During territorial disputes or mating season, males face off in mirrored postures, frills extended, bodies elevated, each attempting to intimidate the other into retreat. Physical combat is rare. Display itself resolves the contest. The same energy-efficient bluff that saves it from predators also prevents injury within its own species. The frill, then, becomes a visual language, one that communicates dominance, readiness, and even temperature state. Infrared imaging shows that active males heat their frills more than females, possibly enhancing the saturation of orange and red pigments through increased blood flow. Color here becomes status. In the greater logic of the savannah, this startle economy fits neatly among Australia's evolutionary experiments. Kangaroos use erratic hopping to scramble pursuit algorithms. Thorny devils deflect attention with false heads. Even the frilled lizard's distant cousin, the bearded dragon, employs darkened throat patches as a form of bluff display. Fear in these systems is not weakness, it is engineering. It creates space, misdirection, and choice where speed alone would fail. Seen through a high-speed camera, the frilled lizard's escape looks less like panic and more like choreography. The frill opens at frame 1. The predator flinches by frame 8. By frame 15, the lizard has already pivoted. Dust explodes behind it as it rises onto 2 legs and sprints upright, tail counterbalancing like a tightrope walker's pole. It does not look graceful. The head bobbles, limbs thrash, but function overrides form. Each stride converts shock into distance, fear into survival. By the time the predator reorients, the lizard is already a dozen meters away, blending into the heat haze. In a world where most creatures rely on pure athleticism to live another day, the frilled lizard demonstrates something subtler, the strategic manipulation of attention. Its defense does not alter the predator's strength or speed. It alters its focus. That momentary redirection is enough to save its life, again and again, across thousands of generations. Evolution here is not about who runs fastest, but who controls the frame rate of perception. And so the question emerges from the red dust and heat shimmer of Australia's north. In the contest between predator and prey, does fear truly beat speed? The frilled lizard's answer, played out in milliseconds and heartbeats, is yes, but only if you understand how to spend it. Fear, when engineered with precision, becomes more than an emotion. It becomes a currency, a brief, brilliant transaction between illusion and escape. Across the open woodlands and suburban edges of Australia, where leaf litter crunches under dry wind and the air shimmers with heat, a flash of impossible blue breaks the monotony of brown and dust. It's a color so sudden, so alien to this palette of ochres and greys, that even seasoned predators hesitate. A blue-tongued skink, thick-bodied, low to the ground, and built like a scaled sausage, has just opened its mouth. Inside that dark cavern of flesh lies its only weapon, a deep cobalt tongue, glossy as enamel, thrust forward in a rapid, vibrating flare. For a heartbeat, it looks venomous, toxic, untouchable. Then the mouth snaps shut, and the lizard vanishes into cover. The entire event lasts less than a second, but that second can be the difference between survival and dismemberment. To the untrained eye, the blue tongue's display seems theatrical, even comical, a harmless reptile pretending to be dangerous. Yet behind this flash of pigment lies a sophisticated evolutionary calculation, the color pop tax. In ecosystems built on fear and recognition, color is currency. A bright warning can buy hesitation, even from an enemy that could easily overpower you. The cost is small, a dab of pigment, a brief display, but the payoff can be enormous. The blue-tongued skink's world is built from ambushes and near misses. It lives on the margins of visibility, foraging through fallen leaves and garden edges for beetles, slugs, and berries. It is diurnal, basking to raise its body temperature into the mid-30s Celsius, the metabolic sweet spot where muscle reflexes and visual processing align. But being active in daylight exposes it to hunters that read every shadow as opportunity: kookaburras, brown snakes, and even feral cats. Against these, the skink has no claws, no speed, and no venom. No, its salvation lies instead in deception, a system so simple that it works precisely because it doesn't have to prove anything. When threatened, the skink inflates its body, hissing loudly as ribs expand to make it seem thicker, heavier, more substantial. The tail, banded in alternating stripes, blurs with the body outline, a decoy that invites a misplaced strike. But the true deterrent is the mouth display, a violent opening of darkness, the sudden electric blue tongue darting forward like lightning. The color contrast alone shocks the eye. The tongue's surface absorbs red wavelengths, reflecting mostly short-wave light that cuts through shadows like a signal flare. Against the dark oral cavity, it reads as unnatural, even chemical. Predators equipped with color vision, especially birds and reptiles, instinctively interpret such color pops as warning signs of toxicity. Many Australian snakes and insects use similar cues, pairing dark bodies with bright flashes of blue, yellow, or orange to advertise venom. The skink hijacks this rulebook. It pays the color tax but never delivers the toxin. In field studies, researchers have quantified the bluff. By presenting predator models, mechanical birds, snake effigies, and cameras simulating optical recognition, to blue tongues with varying pigment intensity, they discovered a consistent pattern. The deeper the blue saturation, the higher the predator retreat rate. With faded or artificially dulled tongues, attacks continued in 70% of trials. With rich cobalt tongues, the rate dropped below 20%. Even more intriguing, predators often retreated before physical contact. The visual cue alone triggered avoidance behavior. The message is clear. In ecosystems ruled by instantaneous decisions, appearance can be more potent than reality. But color comes at a cost. Producing and maintaining that intense hue requires specialized skin structures, not just pigments, but light-scattering nanostructures in the tongue's tissue that amplify blue reflection. These cells, called iridophores, contain stacks of guanine crystals arranged to refract light at specific wavelengths. They demand metabolic investment and degrade over time. Older skinks often display paler tongues, losing some bluff effectiveness, perhaps one reason why they rely more on burrow retreats than confrontation. Evolution thus enforces a subtle economy. Invest enough in color to deter, but not so much that the cost outweighs the odds of being attacked. Behaviorally, the timing of the display is just as critical as its intensity. The skink does not flash its tongue at every disturbance. It waits, motionless, until the predator commits. When the threat crosses a threshold distance, the mouth opens wide, accompanied by a hiss that vibrates through dry grass. The tongue lashes forward, often paired with a forward lunge. This choreography maximizes the bluff's impact. The predator, seeing both color and movement, perceives aggression rather than fear. Then, before the illusion collapses, the skink bolts for cover. It is, in effect, a visual stun grenade. The physiology of the bluff is equally intricate. The tongue's blue color intensifies with stress due to increased blood perfusion under the reflective cells, altering the background absorption and deepening the apparent hue. High-speed imaging shows that the lizard modulates the brightness mid-display. The first flick, bright and short, the second slower, darker, more deliberate. This rhythmic modulation mimics the pulsing color changes of certain venomous species, like coral snakes or blue-ringed octopuses. The mimicry is unintentional but effective, feeding into the predator's mental catalog of danger signals. In ecological terms, this defense is a perfect adaptation for an omnivorous generalist. The blue tongue's habitat overlaps with humans, and its success in suburban Australia proves the bluff still works in a world of dogs, cats, and cars. It is one of the few native reptiles that not only tolerates urbanization, but thrives in it, scavenging garden scraps and basking on warm concrete paths. Even domestic pets, conditioned through thousands of encounters, hesitate before attacking a mouthful of blue. The skink's performance transcends species. Fear, after all, is universal. The evolutionary logic behind this color pop tax has parallels throughout nature. The monarch butterfly's orange wings, the wasp's yellow bands, the poison dart frog's blue skin, all broadcast danger through chromatic exaggeration. The blue tongue, lacking real venom, purchases entry into this visual fraternity through mimicry. Its cost is minimal, a fixed pigment structure, but the reward is safety bought at the speed of perception. This asymmetry makes the system stable. Predators that ignore the warning occasionally pay a lethal price elsewhere, reinforcing the reflex to avoid bright blue wherever it appears. Thus, the skink profits from a shared illusion maintained by others. It doesn't need to be poisonous. It only needs the rumor of poison to persist. Yet the bluff's value is context-dependent. In low light or heavy shade, the blue's spectral edge fades and the warning loses potency. Skinks in darker habitats often rely more on hiss and body inflation than color. Conversely, populations in open, sunlit regions exhibit more saturated tongues, evidence of local selection tuning the color to match visual conditions. This geographic variation underscores the interplay between ecology, physics, and psychology that defines anti-predator design. Even the brightness of the Australian sun becomes part of the equation, sharpening or dulling the illusion as the environment demands. There's also a quiet irony in this adaptation. The blue tongue's most famous feature, its vivid, unnatural color, is rarely seen by those who share its habitat. Humans, mistaking it for a snake or ignoring it entirely, seldom witness the full display. Only in moments of mortal tension does it reveal its secret. Evolution, it seems, built a masterpiece of bluffing not for display or attraction, but for the split-second theater of survival. When viewed in slow motion, the entire sequence unfolds like an optical trick. The sudden gape, the shock of color, the instant recoil of the predator, and the lumbering retreat of the lizard into cover. It's not elegant, but it's effective, a low-cost defense scaled perfectly to the economics of fear. The blue tongue is both shield and signature, a message scrawled in light across the retina of any attacker bold enough to get close. And so the question that hangs over this performance is not just biological but philosophical. How much is a good bluff worth? For the blue-tongue skink, the answer lies in every predator that hesitates, every second bought through color alone. In a land where speed and venom dominate, the skink survives by selling an illusion, one paid for in pigment and timing, but redeemed in life itself. Evolution, ever the economist, has calculated the exchange rate perfectly, one flash of blue for one more day beneath the sun. At the edge of the eucalyptus canopy, the afternoon air trembles with a slow, rhythmic breath. Branches shift, leaves twist, and light breaks into 1,000 green shards that flicker like water. Somewhere in this constant motion, somewhere perfectly unremarkable, hangs an animal that has made invisibility an art form. The stick insect does not hide in the shadows, it hides in plain sight, inside the visual grammar of the forest itself. It is a creature built not to move when it wishes, but only when the wind allows. Its life is written in stillness, and its movements are measured by the gusts that pass through the trees. To the casual observer, the insect is indistinguishable from the twigs around it. Its limbs taper to bark-like points. Its surface is textured with fine ridges and scars that mimic the imperfections of wood. Even under magnification, veins and joints resemble plant fibers. But the illusion goes deeper than shape. What truly completes the disguise is timing, the choreography of motion synchronized to the breath of the wind. When the forest is still, the insect becomes sculpture. When the breeze stirs, it sways gently, not by accident, but by design. Evolution has tuned this mimicry to one of nature's oldest rhythms, the wind that moves everything alive and still in the same frame. This wind-gated motion is not just camouflage, it is sensory strategy. Stick insects possess mechanoreceptors, tiny hair-like structures along their legs and antennae that detect even the faintest air movements. When air pressure drops or surrounding leaves begin to oscillate, these sensors fire. The insect waits for just the right amplitude and direction before taking a step. In laboratory wind tunnel studies, individuals have been observed standing motionless for hours in calm air, only to resume movement precisely when a gust replicates natural forest turbulence. The timing is uncanny. Their gait synchronizes to the oscillation frequency of surrounding branches, ensuring that any shift in outline merges seamlessly into the visual noise of motion around them. The evolutionary logic of this adaptation lies in predator perception. Many birds and reptiles that hunt stick insects rely on edge detection, the ability to identify outlines and motion discontinuities in cluttered environments. A solitary twig that moves against a background of still branches stands out immediately, but a twig that moves with the forest's collective sway becomes invisible. By linking motion to environmental noise, the stick insect exploits a fundamental flaw in its predator's visual systems. They're not built to see the forest and the tree as one. The biomechanics of the insect's sway reveal a marvel of low-energy control. Its long, slender legs act like flexible shock absorbers, transferring minute wind forces through its body without disturbing its center of gravity. Muscles hold minimal tension, allowing micro-oscillations to pass through the exoskeleton naturally, like tremors through a reed. The insect's brain doesn't calculate every sway, it lets physics do the work. When a gust pushes, the insect's entire form yields just enough to stay aligned with the motion of its perch. The illusion is thus not actively maintained, but allowed to happen. In nature, sometimes the most efficient deception is the one you don't resist. This strategy extends even to the insect's reproductive cycle. Females, often larger and heavier, lay eggs that resemble plant seeds, complete with textured casings and small cap-like structures called opercula. These eggs drop to the ground and blend perfectly with the forest floor. Ants, mistaking them for food, carry them to their nests, unintentionally providing protection until the young hatch. From birth, the next generation enters a world defined by mimicry, each stage of life a reflection of something else. The forest doesn't just hide the stick insect, it raises it. The ecological implications of such adaptation run deeper than disguise. Stick insects are herbivores that consume leaves in slow, deliberate bites, their feeding pattern evenly distributed across the canopy. This behavior prevents overstripping of any single plant, spreading damage in a pattern that mimics natural leaf senescence. In a subtle way, their camouflage benefits the forest, regulating pruning without attracting visual attention that might summon predators. Their existence becomes a quiet, ecological handshake. The insect feeds without drawing focus, and the forest, in turn, provides both cover and rhythm. To understand the limits of their invisibility, researchers at the University of Adelaide once constructed wind tunnel experiments mimicking natural gust cycles. Artificial leaves and branch replicas surrounded live insects, while cameras tracked predator response times under varying wind conditions. The results were striking. When the air was still, predatory birds detected motionless insects within seconds. But when gusts matched the insect's movement cues, detection rates dropped to near zero. Even sophisticated image tracking software failed to isolate them. The secret wasn't just the visual disguise, it was timing. Motion that aligns with noise is functionally invisible. This synchronization also shapes behavior beyond camouflage. During courtship, males locate females through subtle vibrations transmitted along branches. These tremors, produced by rhythmic body taps, must be timed between gusts to ensure clarity. The same wind that conceals them from predators can also mask communication. Thus, every action, feeding, mating, even relocating, is bound to the breath of the forest. The stick insect's existence becomes a dialogue with air itself. Move when it moves, stop when it stops. There's an elegance in such restraint, an evolutionary wisdom in knowing that stillness can be strategy. In a landscape where everything is constantly competing for attention, bright plumage, loud calls, swift chases, the stick insect plays the opposite game. It wins by not being seen, not being heard, not being known. Its life depends on the patience to remain absolutely motionless for hours or days, trusting that invisibility is not a passive state but an active discipline. The insect's stillness is not absence of life. It is control so precise that it dissolves into the background. Predator-prey interactions here unfold almost like optical illusions. A bird's eye sweeps across the canopy, identifying potential targets through movement cues. In high-speed footage, the bird's head jerks, halts, then moves on. It never registers the stick insect inches from its beak. The insect doesn't flinch. Only when a breeze passes does it sway, just slightly, to reset its posture or shift position. The predator, unable to distinguish organic sway from artificial motion, remains blind. It's a demonstration of behavioral physics, the alignment of biological decision-making with environmental noise to erase detection probability. Even the color palette of the stick insect plays a role in this optical symphony. Its greens and browns are not uniform, but fractal, micro-patterns of light and shadow that match the bark's irregularities under different lighting angles. Under infrared imaging, their bodies reflect heat similarly to woody stems, minimizing contrast for thermoreceptive predators like snakes. Camouflage here operates across spectra, visible, thermal, and mechanical, each layer reinforcing the illusion that this is not an animal but a fragment of forest anatomy. The paradox of such life is that perfection brings fragility. The same specialization that allows the stick insect to vanish also limits its ability to adapt. Changes in vegetation structure, wind patterns, or humidity can collapse the illusion. In degraded forests or monoculture plantations, where plant forms and airflow homogenize, detection rates rise sharply. What once was artful mimicry becomes a clumsy imitation. In this sense, the stick insect is not just a survivor of the forest, it is a measure of the forest's complexity. Its camouflage works only when the background retains its chaos. As twilight deepens and the wind quiets, the insect freezes once again. The forest stills, the air thickens, and all motion stops. It stands suspended between being and not being, the perfect equation of shape, color, and patience. Nothing about it demands attention, and that is precisely why it endures. To watch a stick insect move is to glimpse evolution's understanding of perception, that visibility is relative, that motion can betray as much as it can save. It teaches that sometimes survival means surrendering control to larger rhythms, letting the environment itself become the camouflage. The insect does not ask when to move, it waits until the forest answers. And so the final question lingers among the branches. When is the best move to sway like a tree? For the stick insect, the answer is simple: only when the wind speaks first. The first sound is water, that slow, perpetual breathing of the creek. Gum leaves drift past like mottled scales, their reflections stitched to the surface until a ripple fractures them. Then a splash, abrupt, deliberate, yet somehow untraceable. By the time the circles spread outward, whatever made the noise is gone. Only if one looks long enough does the shape reveal itself again, not in the water, but on the bank. A reptile, half in shadow, half in light, body angled perfectly along the seam where earth meets stream. The eastern water dragon, Intelligama lesuorii, lives not simply beside water, but inside the edge itself. It is the embodiment of transition, an organism that uses the optical confusion of two worlds to disappear. Along Australia's east coast, from Brisbane's mangroves to Sydney's park ponds, water dragons occupy the narrowest of habitats, the in-between zones. The physics of this setting define their biology. Land and water reflect light differently. Air and surface shimmer, distort outlines and colors. Shadows move in opposite directions depending on the angle of the sun. Most animals avoid this confusion. It disrupts visibility and depth perception, but the water dragon thrives in it. Its camouflage is not a matter of color matching or background blending, but of perceptual misalignment. When viewed through the wavering air above a sunlit stream, its body edges dissolve into static. It is not invisible exactly. It is unreadable. The dragon's coloration is a map of its habitat's contradictions. Its back is dark olive and brown, the hue of wet bark and sunburned soil. Along the flanks, lighter bands mimic rippled reflections. The underside fades into pale cream, merging with light refracted off the water's surface. This vertical gradient, dark above, bright below, mirrors the way light behaves at the boundary between mediums. When it basks half submerged, the portion above the water reflects sky. The portion below is shadowed by the riverbed. Viewed from any angle, its outline fractures. Predator vision studies using contrast mapping cameras confirm this. Edge detection algorithms, which mimic avian sight, fail to distinguish the lizard's body when half of it occupies the light-splintered surface plane. In visual terms, it ceases to exist at the seam. Behaviorally, the water dragon exploits this optical chaos with precision. It spends most daylight hours perched just above the waterline, on a root, log or slanted rock, always within one tail flick of safety. Its posture is calculated. Forelegs braced, hind legs tensed, tail submerged to sense vibrations. When disturbed, it dives instantly, staying under for up to half an hour, thanks to its slow metabolism and air stored in the lungs and throat cavity. Yet its escape is not panic, but protocol. In many encounters, the predator, whether a kookaburra or a feral cat, hesitates after the splash, unsure of what it saw. To the hunter's eye, the lizard didn't leap from the log. The log itself seemed to collapse. This manipulation of perception relies as much on physics as on instinct. The boundary blur effect arises because the surface of water acts as both mirror and window. Light bouncing off sky and vegetation overlays the submerged scene, producing a shifting mosaic of contrast. To a predator scanning from land, this mosaic is visual noise. The dragon's mottled scales reflect these colors in fragmented patches, amplifying the chaos rather than resolving it. Its camouflage doesn't erase its image, it overpopulates it. Edge detection in animal vision depends on continuity, lines that define form. The water dragon breaks those lines at precisely the scale where the human and avian eye are least effective. In controlled trials, biologists filmed dragon models of varying brightness positioned at different distances from water. When edge contrast between land and water was highest, clear reflections, bright midday light, detection errors peaked. Predators struck at shadows, ripples, or the dragon's reflection rather than the body itself. The lizard's survival strategy, then, is not to vanish, but to force miscalculation. By aligning itself with the border between reflective and absorptive surfaces, it weaponizes confusion. The interface between air and water becomes a living cloak. The water dragon's physiology reinforces this amphibious existence. Its scales are semi-permeable to heat, but resistant to waterlogging, allowing it to thermoregulate on the edge. When basking, dorsal scales absorb radiation efficiently. When submerged, water rapidly conducts excess heat away. This balance enables longer basking without overheating, crucial for an ectotherm that alternates between open banks and cold streams. Its nostrils close underwater, and a specialized nictitating membrane shields its eyes without obscuring vision, giving it clarity both above and below the surface. In the literal sense, it sees the boundary more clearly than most creatures do. Juveniles take the strategy even further. Smaller, more vulnerable, they spend more time among surface vegetation, floating mats of leaves or reeds, where dappled light and moving reflections compound the blur. They are not fast, but their first line of defense is optical, staying where no single visual rule applies. Predators adapted to either land or water face the same problem here. The prey exists in both domains but commits to neither. In ecological terms, it occupies a perceptual refuge, a place where detection algorithms, whether biological or mechanical, lose traction. This habitat preference influences every aspect of its behavior. Feeding takes place at the border too. Water dragons hunt insects, small crustaceans, and fallen fruit, all items that accumulate at edges. Even their social interactions, from head-bobbing displays to territorial chases, happen where reflections distort size and speed perception. Dominant males often position themselves directly above mirrored surfaces, their gestures doubled by reflection. In confrontations, this optical amplification can deter rivals without physical conflict, much as the frilled lizard's display bluffs strength through illusion. Evolution across species seems to reward mastery of perception as much as mastery of muscle. The blurred boundary also defines the dragon's predators. Herons strike from above using refraction to their advantage. Snakes ambush from below. But even they are occasionally fooled. Under calm conditions, the lizard's reflection appears sharper than the body itself, causing strike errors. Infrared footage shows predators aiming fractionally off-target, attacking the reflection rather than the animal. In evolutionary time, such consistent perceptual misfires can shift predator populations or behaviors, subtly reshaping ecosystems. The water dragon's camouflage, then, is not merely self-preservation. It influences the entire predator-prey dynamic along the Australian riparian corridor. Yet this delicate balance depends on environmental quality. Pollution, siltation, and altered light angles from urban construction all change surface reflectivity. Where water becomes opaque or shadowed, the boundary blur fails, outlines return, and predation rates rise. In natural clear streams, however, the phenomenon is almost perfect. Viewed through polarized lenses that simulate avian vision, a basking water dragon dissolves into visual static, its outline no sharper than a reflection of leaves. Only motion, a blink, a tail flick, betrays its form. There's a quiet elegance to the dragon's life within this optical threshold. Its very name evokes myth, but its behavior is mathematical. Every placement, every pause, every dive is governed by light geometry and contrast ratios. Unlike the crocodile, whose dominance lies in raw stealth, or the goanna, which depends on speed, the water dragon survives by confusion, not hiding in darkness, but in ambiguity. It occupies the line that the eye cannot resolve, the margin where two realities overlap. In cinematic terms, this is the lizard's stagecraft. When the morning sun hits the water at an angle of about 30 degrees, glare becomes intense. The dragon uses this hour for basking. By midday, as reflections flatten, it retreats into partial shade or the shallows. In the afternoon, when ripples lengthen and contrast returns, it emerges again. Its circadian rhythm is synchronized not just to temperature, but to optical conditions, a daily dance with visibility. To watch one up close is to see evolution's subtle understanding of physics. As it climbs from the water, droplets cling to scales like beads of glass, refracting light into tiny prisms that further distort outline and color. When it freezes in half-light, the surrounding reflections reclaim its body, folding it back into the scenery. In these moments, it seems less like an animal and more like an echo of the landscape, something the creek imagines into being, then reabsorbs. So much of survival in Australia's ecosystems comes down to extremes: heat, venom, speed. The eastern water dragon shows another path: survival through uncertainty, through the exploitation of perception itself. It does not flee from clarity or chaos, but finds safety exactly between them. The water's surface, that thin optical membrane separating sky and soil, becomes its fortress. And so the question remains, shimmering like the creek it inhabits: is the seam the safest place? For the water dragon, the answer lies not in the choice between land or water, but in the mastery of their meeting point, a life lived in the blur where the world can't decide which side it's on. In the filtered light of the Australian forest floor, where sunbeams break into fragments through overstory canopies of eucalypt and wattle, every leaf is a brushstroke in a living mosaic. The ground shimmers in constant flux, patches of brightness from shifting sky windows, shadows layered over bark, dust, and dry grass. It is here, amid this fractal landscape, that one of Australia's most adaptable ambush predators has mastered the art of invisibility, not through color alone, but through scale: the carpet python, Morelia spilota, an animal that hunts by matching itself to the visual geometry of its background. To see one is to experience uncertainty. The snake's pattern, a complex tapestry of gold, olive, charcoal and cream, looks like randomness at first glance, yet carries a precision that the untrained eye misses. Each blotch and band mirrors the average size and spacing of leaf litter on the forest floor. The python does not simply lie upon the background, it becomes a statistical extension of it. This phenomenon, known to behavioral ecologists as patch map matching, describes a predator's ability to position itself where the scale of environmental patterns aligns perfectly with its own. For the carpet python, the camouflage is dynamic not because its skin changes, but because its choice of ground does. Imagine the forest through a predator's lens, a goanna's flickering tongue tasting the air, or a bandicoot's darting eyes scanning for movement. To them, pattern detection relies on contrasts and edges, sudden shifts in tone, brightness, or texture. A well-camouflaged python reduces these differences. It selects resting sites where its blotches fit the grain of the background, so that every transition on its body corresponds to one on the forest floor. It's a living algorithm tuned to the visual scale of decomposition. When it coils under a fallen log or along a bed of mixed gum leaves and soil, each patch of its skin aligns to an environmental patch of roughly equal size. The result is a perfect visual overlap. No single pattern stands out long enough for a brain to resolve snake. Field biologists have tested this hypothesis using high-resolution imagery and computational models. They mapped forest floor textures and overlaid images of carpet pythons in varying habitats, then measured edge variance, a metric for visual detectability. The findings were striking. Pythons that selected leaf litter with patch sizes matching their dorsal pattern were detected by predators and prey only half as often as those placed on mismatched substrates. In experimental enclosures, prey animals froze or fled less frequently when a python's background matched its internal pattern frequency. In effect, the environment completes the snake's disguise. The pattern doesn't just hide the predator, it chooses its hunting ground. Every movement of the python reflects this mathematical harmony. When active at night, it glides silently over uneven terrain, the belly scales gripping bark or gravel with a subtle ripple. Before dawn, it selects an ambush site, a place of high pattern congruence. This might be a pile of dry leaves near a creek bend, a rock and shadow patch beneath a paperbark trunk, or even the mottled dirt of a kangaroo trail. Once chosen, the snake holds still for hours, sometimes days, its thermoregulatory control allowing it to maintain readiness with minimal metabolic cost. Even its breathing becomes synchronized to ambient motion, small enough that swaying branches or insects crossing the litter mask the rhythm. The evolutionary payoff for such precision is enormous. In the heat of northern Australia, many ambush predators face the same paradox. To stay hidden, you must stay still. To stay alive, you must stay cool. The carpet python resolves this by using the very micro-habitats that suit its camouflage: leaf piles, hollow logs, shaded gullies, which also moderate temperature extremes. By choosing a site that visually conceals and thermally stabilizes, the python optimizes both hunting success and energy balance. Ambush ecology here merges physics and physiology. Camouflage becomes not a surface pattern, but a full environmental equation. Predation events reveal how powerfully this system works. A small wallaby or brush-tailed possum may graze only meters from a coiled python without alarm. Infrared footage shows the predator remaining utterly motionless until a precise moment when movement within strike range crosses its heat-sensing threshold. The attack itself is explosive, a blur of coils and muscle that erupts from stillness. But just as remarkable is what follows. After the kill, the python drags its prey deeper into shadow, realigning itself among similarly scaled background patches, as if resetting the camouflage. Even digestion happens under pattern cover. The swollen body finds new geometry to match. For the prey community, this invisible predator creates a behavioral filter. Species that feed in high-contrast areas, open sand, bright grass, rarely fall victim. Those that forage where light and shadow intermingle bear the highest risk. Thus, the python's camouflage doesn't just hide it from individuals. It shapes the ecological geography of fear. Certain zones of the forest become quiet, others lively, all because of how pattern scale dictates safety. Researchers exploring this dynamic have used artificial snakes painted with different blotch scales and placed them across mixed habitats. The results confirmed what evolution already knew. Detection time varied directly with how closely the model's pattern matched the substrate's patch frequency. Too fine, and the pattern blended into uniformity. Too coarse, and edges betrayed form. The natural python's design sits precisely at the median. A Goldilocks geometry evolved through millions of successful hunts. The mechanism behind this matchmaking is partly visual, but also behavioral. Carpet pythons possess excellent environmental memory. They reuse successful ambush locations seasonally, returning to the same logs or clearings where both pattern and prey align. Some individuals have been recorded occupying the same site year after year, waiting for the same seasonal cycles of birds or mammals to pass through. The predator, in this sense, becomes part of the habitat's rhythm, a recurring contour within the forest's visual language. Thermal imaging adds another dimension. The snake's blotched coloration doesn't just mimic pattern, it modulates heat. Darker patches absorb more solar radiation, creating microthermal gradients along its body. When partially exposed to sunlight through foliage, these gradients help the python balance temperature without revealing its shape. The mosaic of warm and cool spots on its skin mirrors the thermal heterogeneity of leaf litter. To infrared vision, as possessed by some of its prey, the camouflage persists even beyond visible light. It is a deception built across spectra, calibrated to both eyes and heat sensors. In evolutionary terms, such specialization speaks to a long history of co-adaptation between predator and environment. Australia's forests have burned, regrown, and restructured countless times, yet the python's generalist pattern remains effective across this shifting mosaic. Its camouflage is resilient because it is scalable, effective at multiple spatial resolutions. Whether it lies among the large debris of dry sclerophyll forests or the finer litter of coastal rainforest edges, its body fits. That adaptability explains why the carpet python thrives in settings as varied as suburban gardens and mountain gullies. Wherever pattern exists, it can find a match. This relationship between predator and background blurs the line between passive adaptation and active choice. Does the python simply benefit from the forest's patchiness, or does it select the very textures that complete its design? Observational evidence leans toward agency. In choice experiments, individuals consistently preferred substrates with visual statistics similar to their own body pattern. The snake, through sensory feedback and experience, learns to recognize its best hiding places. It is a visual strategist, not merely a static participant in camouflage. At dusk, as the cicadas pulse and the air cools, the forest's patchwork shifts again. New shadows stretch across the ground, and the python must re-evaluate. Its scales catch faint moonlight in broken flashes. Its body adjusts by inches. The pattern realigns. In these moments, the boundary between organism and environment becomes conceptually thin. The snake is no longer distinct from its surroundings. It is a component in the forest's optical code, an equation of pigment, light, and geometry balanced precisely for deception. To watch this unfold under night vision cameras is to witness how invisibility functions as a form of intelligence. The python's camouflage is not static like a leaf insect's, nor reactive like a cuttlefish's. It is contextual. It depends on choice, timing, and spatial logic. Every coil placed, every degree of angle adjusted, recalibrates how the world perceives it. The python doesn't vanish by magic, it vanishes by mathematics. So when the question arises, does the pattern choose the prey? The answer, in a way, is yes. The pattern defines where the snake will lie, and where it lies determines which prey will pass within reach. The geometry of leaves and light, once mere backdrop, becomes the architect of opportunity. Here, survival is not won by strength or speed, but by precision of place. The carpet python's greatest weapon is not its coil or bite, but its flawless alignment with the chaos beneath the trees, an ancient partnership between body and background that makes the hunter invisible until the forest itself decides to move.